Okay, for three equation system in differential equations, we have, in this example, we're looking at solving for x of 1, x of 2, and x of 3. And we have, among the equations, we have the first order derivative of x of 1 is equal to 2 times x of 1 plus x of 2 minus x of 3. And we have for the first order derivative of x of 2, we have set equal to negative 4 x of 1 minus 3x of 2 minus x of 3. And for the first order derivative of x of 3, we have equal to 4 times x of 1 plus 4 times x of 2 plus 2 times x of 3. And again, setting up the coefficient and identity matrices. Okay, so we have column by column, we have in the coefficient matrix, we have coefficients of the x of 1, then the x of 2, and finally the x of 3 terms. And for the identity matrix, again, we're starting with 1 in the upper left-hand corner and just having repetition of 1 running diagonally. And once again, we have zeros surrounding the ones that are formed. And in looking at the setup for the determination of the eigenvalues, again, we're looking at the determinant a minus lambda I set equal to 0. And for this particular three equation system, and looking at the determination of the eigenvalues. And again, I'm going to find out what we have in the determinant for this 3x3 system. And I'm going to go column by column. Okay, so we have for the odd number column values, I'm going with no sign changes. So, and we have anything that is in the even column position, I'm going to be taking the opposite sign. So working with the top row, we have the first set of elements, we have 2 minus lambda. And I'm going to multiply by the 2x2 determinant formed by the elements outside of any row or column that 2 minus lambda shares. Okay, so outside the top row and the first column, we have 3 minus lambda, negative 1, 4, and 2 minus lambda. And then we have minus 1. Okay, we have, in this case, all right, for the 2x2 determinant, these will come from elements that are not inside the top row or the middle column. Thus, we have negative 4, negative 1, and also we have from the bottom row, from the first and last columns, I have 4 and 2 minus lambda. And then we have crossing over, we have plus, and we have in the last column, we have the heading at negative 1, and forming a 2x2 determinant from the elements that do not exist in the top row or the last column. I have negative 4, negative 3 minus lambda, 4, and 4. And carrying out, okay, so we have 2 minus lambda, and again we have the 2x2 determinants. Okay, have again this collection. Then we have minus 1 times what we're going to have for the next 2x2 determinant, and we have plus minus 1. And again, we have the 2x2 diagonal products to combine, and just kind of cutting to the chase. Once you combine your elements, we're going to have negative lambda cubed plus lambda squared minus 4 lambda plus 4 is equal to 0, and just changing the signs. Okay, now this is a case of where we can factor by grouping. Okay, and so we have between the first two terms, lambda squared is the greatest common factor. And for plus 4 lambda minus 4, 4 is the greatest common factor. And notice that for lambda cubed minus lambda squared goes into it lambda minus 1. And for lambda minus 4, 4 into that combination is also going to be lambda minus 1. So we have from the factoring by grouping, okay, we have lambda minus 1, which is the shared factor. And the other factor we have coming from combining the outside terms and operation, where we have lambda squared plus 4. And we have with the zero product property from lambda minus 1, we'll let this result be the first eigenvalue where we have equal to 1. And for lambda squared plus 4, now we're going to have additive inverses, okay, for this value lambda. And we'll say that for the second eigenvalue, we have at 2i. And again, with the bar over lambda 2, that is going to be the conjugate, which we have at negative 2i. And you could also have it as lambda 2 equal to negative 2i, and the conjugate to be at positive 2i. Now, crossing over to the stage that we have in the determination of eigenvectors. All right, and again, so we had the product of A minus lambda I, the matrix of that times the eigenvector is equal to 0. And working with the first eigenvalue of 1 and just plugging into what we had set up for A minus lambda I. Okay, we have this 3 by 3 matrix, and we have times A of 1, B of 1, C of 1, which represent the first eigenvector, and we have is equal to, again, the 3 by 1 representation of 0, and just taking a little bit of a shortcut. Okay, so you have 1a1, 1b1, minus 1c1 is equal to 0. And since we're dealing with integers and real numbers, we'll take this little bit of a shortcut and arrive at the reduced row echelon form. And here with the 1, 1, 0, and 0 running across, this will signify that a of 1 plus b of 1 is equal to 0. And so you're going to have that a of 1 and b of 1 will have an additive inverse relation, where one is going to be the opposite sign of the other. Now from the second row, we have that c of 1 is equal to 0, and so c of 1 is negligible. And since a of 1 and b of 1 are of opposite sign, now you could say that a of 1 is at negative 1 and b of 1 is at positive 1, but we'll just say that v of 1 is equal to, where we have running down, okay, we have 1, negative 1, and 0. Now, in the crossover to working with the second eigenvalue and designating 2i, so you have, again, so you have this set up here, and now we won't have the luxury of working with the shortcut and a typical calculator since we're dealing with complex numbers. And setting up equations, okay, so you have like 2 minus 2i mapped with a of 2, you got 1 with b of 2, negative 1 with c of 2, and if I form another equation, you have negative 4 with a of 2, negative 3 minus 2i with b of 2, minus 1 with c of 2. And we have a third equation working with the bottom row, so you have this 4 maps with a of 2, the next 4 maps with b of 2, and 2 minus 2i maps with c of 2. And trying to provide a link among a of 2, b of 2, and c of 2, which will be the coefficients of the second eigenvector. If I start out subtracting this second equation from the first, now the c of 2 terms will go out, and so you'll have a of 2 and b of 2 sort of battling it out. And just taking what we have here, we have complex coefficients where we have 6 minus 2i quantity times a of 2 is equal to negative 4 minus 2i quantity times b of 2. And we can say that for what we have with a of 2, okay, we'll see that will be negative 4 minus 2i. And for b of 2, we'll let this be 6 minus 2i. Think of it like this. 6 minus 2i times negative 4 minus 2i is equal to negative 4 minus 2i times 6 minus 2i. And in looking for c of 2, okay, we can adopt from equation 3. Now we have a of 2 and b of 2 determined, and we have c of 2 to form or to develop, and leaving the c of 2 expression by itself and moving the other terms over, we have 2 minus 2i quantity times c of 2 is equal to negative 8 plus 16i. And then dividing by 2 minus 2i, we have negative 8 plus 16i all over 2 minus 2i. Here we have even numbered coefficients, and we can just take half of everything and still lie in the same proportion. We have negative 4 plus 8i over 1 minus I, and then getting it into a standard complex number, okay, we can take the ratio and multiply by 1 in the form of the conjugate of the denominator divided by itself. And for c of 2, this will lower to negative 6 plus 2i. So we can say that for the second eigenvector for a of 2, b of 2, and c of 2, we have these complex numbers in standard form. And now with our two eigenvectors set up, we can look at solving for x. And we have, again, in the big picture, we have x is equal to constant times the eigenvector times e to the lambda t. And we have two eigenvectors, two distinct eigenvalues to work with. And so just filling in, we have, again, you have c of 1, v of 1, and again, lambda 1 was at 1. And again, we have c of 2, v of 2, and lambda 2 was at 2y. And for e to the 2it, again, we can utilize what we have for Euler's equation, which will go to cosine of 2t plus I sine of 2t. And so just rewriting e to the 2it in terms of the Euler equation identity and acknowledging that I squared is equal to -1. Once we cross over, we have for x of 1, taking the top layers, we have c of 1 e to the t, and we have minus 4c2 cosine of 2t, minus 4c2 I sine of 2t, and then working with -2i, we have -2c2i cosine of 2t, and we're going to have -2c2i squared, and -2 times I squared, which is -1, comes out to a positive 2. C2 sine of 2t, and just taking what we have for the middle and lower layers. Middle layer, we have our x of 2 terms, so we have negative c of 1 e to the t, and distributing, foiling out what we have throughout, and distributing c2 over. We have these subsequent terms to follow. Likewise, we have with x of 3, there's no c of 1 term, so everything comes from c of 2. And we have for anything that has c2i, we'll let this be a third coefficient. So if we let c2i be equal to c of 3, we're going to have one way that we can write the general solutions for x of 1, x of 2, and x of 3 is that for x of 1, we have c1 times e to the t, and we have plus c2, and we have times the quantity of -4 cosine of 2t plus 2 sine of 2t. And what was originally attached was c2 and I, we just rewrote as c of 3. And here we have times the quantity of -4 sine of 2t minus 2 cosine of 2t. And for x of 2 of t, again, we have -c1 e to the t plus c2 times the quantity of 6 cosine of 2t plus 2 sine of 2t. And we have plus c of 3 times the quantity of 6 sine of 2t minus 2 cosine of 2t. And then we have last, as a general solution for x of 3, we have c of 2 times -6, or I should say times the quantity of -6 cosine of 2t minus 2 sine of 2t. And we have plus c of 3 times the quantity of -6 sine of 2t plus 2 times the cosine of 2t.